All right, in this lesson, we are going to review how to graph polynomials and rational functions, starting with polynomials. And so when we're graphing polynomials, we need to know what is happening on the end behavior. And for that, we look at the degree of the polynomial and the leading coefficient. And so if your degree, well, let's start with leading coefficient being positive. So if your leading coefficient is positive, the right side of your polynomial is going to be up. And so you don't know really what's happening in the middle, but you know the right side is opening up, regardless of the degree. Right side up. Okay, if the degree is odd, the left side is not going to match. And so left side will be down. If the degree is even, the left side will be the same as the right side. Okay, and so looking at the case where the degree or the leading coefficient is negative, in that case, your right side is down. And then if the degree is odd, left side will not match. And if the degree is even, the left side will match. Okay, and so leading coefficient positive, right side up. If leading coefficient is negative, right side down. The leading coefficient tells you what the right side is doing. And then if the degree is even, left side matches the right side. If the degree is odd, they're the opposite. Okay, and the other thing we have to remember is how to classify our roots or our zeros. If you have the factored form of a polynomial and a factor appears one time, it is going to cross. Sometimes we call that a cut. It is going to cross at that zero. If the multiplicity is even, so say 2, say you have like x minus some number squared, it's going to bounce. And you can kind of picture your quadratic there. And then here you can kind of picture your linear. It's going to cross. And then if your multiplicity is odd but still bigger than 1, so let's say cubed, it is going to twist. And some call that a flatten. And so kind of picturing your cubic function. So the function has a change in concavity at that point. Okay, and so looking at our first example, it is factored for us. And so we can imagine what it would look like if we multiplied all of this out. We would have an x cubed, we would have an x times an x. And so we would end up with an x to the 5 as our first term. And because all the coefficients are 1, we know the coefficient would be 1. And so because the leading coefficient is positive, we know the right side is going to be up. And then because our degree is odd, it's degree 5, we know that left side will not match. And so left side will be down. Okay. And so just picturing the end behavior, right side up, left side down. Next, we need to find all the zeros. And so from this factor, we get -4. And it has a multiplicity of 3. Looking at the exponent. Here, we're going to have x equals -2 with the multiplicity of 1 because there's no exponent, so there's a 1. And then we're going to have x equals positive 1, also with the multiplicity of 1. And so with the multiplicity of 3, we know we're going to have the twist at x equals -4, and then we're going to have a cross at both -2 and 1. So graphing those, we have -4, -2, and 1. Okay, so at -4, there is a twist, and so I like to go ahead and get the end behavior on the graph, and so we know right side is up, and we know left side is down. And then starting at -4, that's where it twists or flattens, and so something like that. And then it doesn't matter how far you go up before you come back down to the -2, and so go up as high as you want, and then at -2 it crosses, and then at 1 it also crosses. Okay. On number 2, it's not factored for us, but that helps us see the leading coefficient is -1 and our degree is 4. We don't have to add up all the different factors in their exponents. So just looking at the 4, this is the leading coefficient is negative, and so we know the right side is down, and then the degree is even, and so we know that the left side is also going to be down. It's going to match. And so just picturing this, right side down, and then left side also down. Okay, and so in order to get our roots, we need to factor this, and so I'm going to rewrite it down here, -x4 plus x3 plus 2x squared. And so whenever your leading coefficient is negative, you definitely want to factor out a negative. And then we also have an x squared in common to each term, so we can factor out an x squared. And so that would be positive x squared minus x minus 2. And then that's just a quadratic that factors to x minus 2, x plus 1. And so there's our factored form. And so whenever you don't have a plus or minus number after the x, even if it's x squared, x equals 0 is the root. You could picture that as x minus 0 squared. And so this has a multiplicity of 2. And so we know it's going to bounce right there. And then we also have x equals 2 and x equals -1. And each of these have a multiplicity of 1. And so it's going to cross at both of these. And so -1, 0, oh, that was -2. -1, 0, and 2. So let's get the end behavior. Right side is down, and left side is also down. And then going from left to right, -1 crosses, and then we're gonna immediately bounce. And so cross, let me do better than that. So we need to cross at -1 and then bounce at 0. So cross, bounce, and then cross again. So something like that. Okay, next we're going to review rational functions. And so when you're dealing with rational functions that have numerators and denominators, you want to factor both the numerator and the denominator. If you have a common factor, you know there is going to be a whole at that factor. So if x minus c, if you have a common factor in both the numerator and denominator, and that's when you have the whole at whatever x value makes that equal to 0. And so once you've identified the whole, you want to use simplified form to identify your vertical asymptote. And so the vertical asymptote is when the denominator equals 0. And you want to get that common factor out. Otherwise, you're going to say there's a hole where there's a vertical asymptote. And then to find the horizontal asymptote, you have to look at the degree of the numerator and the denominator. If it's bigger on bottom, if the degree is bigger on bottom, y equals 0 is automatically horizontal asymptote. So that's what BO stands for. Bigger on bottom, y equals 0. The BOTN, bigger on top, means there is no horizontal asymptote. And then the EATS DC stands for exponents are the same, and the DC stands for divide coefficient, divide the leading coefficient. Okay, and then when you have the bigger on top case, if the degree of the numerator is exactly one more, so x squared over x, or even x cubed over x squared, then you're going to have what is called a slant asymptote. So exactly one more means you're going to have a slant asymptote, and you have to use long division to find the equation of that asymptote. X-intercepts are when the numerator is equal to 0. When the denominator equals 0, that's your vertical asymptote. And then your y-intercept is when you plug in 0 for x. I call that killing the x terms. Okay, and so we're going to do 2 examples. And so first, we're going to factor. And so on top, that's just linear, so there's nothing we can do with that. And then on bottom, that's a difference of squares, x plus 3, x minus 3. And so we do have a common factor. The common factor is x plus 3. And so that means we're going to have a hole where x plus 3 equals 0. If we solve that, it's x equals negative 3. And so we have to go back to the simplified form. So there's nothing left on top, so 1 is a placeholder, and then we only have x minus 3 on bottom. We have to use the simplified form for the rest of our attributes. Simplified form. Okay, and so to find the y value of the hole, we have to plug in negative 3 into that function. And so x is now negative 3, and we still have the minus 3. And so the y value is negative 1, 6. And so you write the hole as an ordered pair. Negative 3, negative 1, 6. And so negative 3, negative 1, 6 is going to be really close to the x-axis because negative 1, 6 is really small. Okay, and so since there's no spot to write the hole, I'm going to write it under the other points. Negative 3, negative 1, 6. It kind of serves as a point because we know the function is going to be over in that quadrant. Next, we can find the horizontal asymptote. And to find the horizontal asymptote, I like to remember that HA, H-A, stands for the funny acronym Bobo Botten Eats DC. And so in this case, it's bigger on bottom. You could look at the original for this and see that we have degree 1 over degree 2, or you could look at simplified form because we just canceled one factor on both the top and bottom. And so either way, it's bigger on bottom. And in that case, y equals 0 is our horizontal asymptote. And so that y equals is very important, otherwise it doesn't read as a horizontal line. So y equals 0 is our horizontal asymptote. And then to find the vertical asymptote, x-intercept numerator equal to 0. And then vertical asymptote is denominator equal to 0. And so looking at our simplified form, our denominator is x minus 3. Don't go back to the factored, the ones with the x plus 3, because that's the whole. And so x minus 3 equals 0. And so x equals 3 is our vertical asymptote. So the x equals 3 is important. The x equals, that means you're crossing through the x-axis. And so we have a vertical asymptote at x equals 3. For our x-intercept, the numerator is just a 1. And I can't say that enough. Don't go back to this original form, otherwise you're going to say the whole is an x-intercept. And so we only have a 1 left. And so since 1 can't equal 0, there is no x-intercept. For the y-intercept, we plug in 0 for x. Okay, and so plugging in 0 for x gives us a -1/3. And so 0, -1/3 is our y-intercept. Okay, and so to finish our graph, we have a part of the function on each side of the vertical asymptote. And so we have 2 points to the left of our vertical asymptote, so we can already tell what's happening to the left. It's going to go through the hole, it's going to go through the y-intercept, and then also follow the asymptotes. Okay, and so for the right side of the vertical asymptote, we need to figure out, is the graph up here or is the graph down here? It can't be both, because then it would fail the vertical line test. And so we just need to pick one of these x values to plug in. I usually pick values close to the vertical asymptote so the numbers stay smaller. And so the point I am going to test is 4. And so when we plug in x equals 4, using the simplified form, 1 over x minus 3 would be 1 over 1, which is just 1. So our ordered pair is 4, 1, and we'll put that on the other points line. And so we know the graph is going to be above the horizontal asymptote. Okay, and so for domain and range, for domain we need to skip over the vertical asymptote and also the hole. Okay, and so as we scan from left to right, the first value we have to exclude is the x value of this hole. And so there's a hole at -3, and so we're going to go from -infinity to the hole, and then we're going to pick back up on the other side using parentheses because we don't equal the -3. We're skipping over it. And then after we skip over that -3, we run into the vertical asymptote, which is at +3. And then we pick back up on the other side of 3, and it goes to infinity. That's this part here. Okay, and so we have to do something similar with the range. We have to skip over the y value of the hole, and then we have to skip over the horizontal asymptote. So we're going from -infinity, and the first place we have to skip is the hole. That's the first value that's excluded. And so we found that value to be -1/6. And so we're going from -infinity to -1/6, and then pick back up on the other side. And then we have to skip over the horizontal asymptote, which is sitting at y equals 0. And then pick back up on the other side, and then it goes on to infinity without any more interruptions. Okay, and so this -1/6 was the hole. This 0 was the horizontal asymptote. For the domain, the -3 we skipped over was the hole, and then the 3 was the vertical asymptote. Okay, last one, looking at number 4, we need to factor. And so looking at the numerator, it says 1 minus x squared. That's not really the right order. We always want our variable first. So I'm going to flip the order. And then when the leading coefficient is negative, factor out the negative. And then you'll recognize we're dealing with the difference of squares. And so we have negative x minus 1, x plus 1. Since there's no common factors, there's no holes to worry about. And so we're ready to go ahead and find our asymptotes. And so looking at the horizontal asymptote, that's the funny acronym. I like to look at the unfactored form. And so we have degree 2 over degree 1. And so this is bigger on top. Whenever it's bigger on top, that's none. That's no horizontal asymptote. But notice we are bigger on top by exactly 1. So there is a slant asymptote. And so that's when I'm going to go to find the slant asymptote so I don't forget. And so to find the slant asymptote, we use long division, and we go ahead and use the unfactored form to set that up. And so our dividend is negative x squared plus, we're missing an x term, and then we are dividing by x minus 2. Okay, and so negative, if you want to fill in the 1, negative 1x squared divided by x is just negative 1x. And then negative 1x times x would get us the negative 1x squared. And then negative 1x times negative 2 is positive 2x. Draw your line, change your signs to subtract. And so that leaves us with a negative 2x plus 1. And so next, negative 2x divided by x is negative 2. And that's as far as you have to go. You don't care about the remainder. You just care about this equation, the slope and the y-intercept, which is negative 1x minus 2. And so we have a slant asymptote at y equals negative 1x, and you can just write negative x minus 2. And so how that looks on the graph is you have a y-intercept of negative 2, and the slope is negative 1. So down 1 over 1, down 1 over 1. And this line doesn't actually show up on your graph. If you were to graph this using Desmos or your graphing calculator, you're not going to see a big slanted line, but you will see the behavior of the function following this line. And so I'm going to graph it in a highlighter like I do the other asymptotes. Okay, next we can find the vertical asymptote by setting the denominator equal to 0. And so our denominator of this function is x minus 2. And so x equals 2 is the vertical asymptote. Crossing the x-axis at 2. And then that's all for asymptotes since we didn't have a horizontal asymptote. For our x-intercept, we set the numerator equal to 0. And so our numerator, we have two factors, x minus 1 and x plus 1. That negative isn't going to affect our solutions. We still just look at our factors that have x involved. And so x equals 1 and x equals negative 1. And so writing them as ordered pairs so they don't look like asymptotes, we have two x-intercepts. And so negative 1, 0, and 1, 0. Negative 1, 0, and 1, 0. And then lastly, for the y-intercept, we just plug in 0 for x. You can go back to the original form, or you can use the factored form. I'll just keep using the factored form. And so negative, and then plugging in 0 to both factors of the numerator, and then plugging in 0 to the denominator. We end up with a negative 1 times 1 over negative 2, which becomes positive 1 over negative 2, and so negative 1/2. And so 0, negative 1/2 would be our y-intercept. Sometimes it's easier from the unfactored form just to look at what doesn't have the x, negative 1/2. And so we can see what's happening to the left of our vertical asymptote. We have these 3 points, and so they're going to follow this red asymptote, and then they're going to follow the blue asymptote. And so that's all we're going to have to the left of our vertical asymptote. We can't have anything down here because then it would fail our vertical line test. And so you only have graph to the left and right. And so we've already figured out the left. We just need to figure out what's happening to the right. And so we need to plug in maybe 3, we could plug in 4, we could plug in 5. I'm gonna go ahead and just plug in x equals 3. And so I'm gonna plug that into, I think I'm gonna do the unfactored form. It's negative x squared plus 1 over x minus 2, and we're plugging in 3. And so 3 squared is 9, still have the negative, and then 3 minus 2 is 1. And so that simplifies to negative 8 over 1, which is just negative 8. So we have the point 3, negative 8. 3, negative 8 is right here. And so we know that the other part of this function is going down towards the red and then also following the blue. Okay, and so the domain of our function, just scanning from left to right, the only interruption, so it's going to go all the way to negative infinity following the blue line, but it's not going to cross the red asymptote. It picks back up on the other side and goes to positive infinity following this blue line. So slanted asymptotes don't actually interfere with your domain or your range. Only vertical and horizontal asymptotes do. And so our domain is going from negative infinity till the vertical asymptote at 2, and then it picks back up on the other side. And we don't have any holes to skip over, and so just that vertical asymptote. For the range, this one's actually pretty hard because you have to figure out what these extrema values are, and we don't yet have the tools to figure out what these max and mins are, and so we can go ahead and just skip the range for now. You will do that in either pre-cal or calculus.